Imagine holding a single tiny particle in your hand. Now imagine another particle, its twin, sitting on the surface of Mars. If you nudge the one in your hand, its Martian twin flinches at the exact same moment. Instantly. This ain't sci-fi. It's a real phenomenon in our universe. It baffled Albert Einstein, who called it spooky action at a distance. As a 30-something with a bit of a Western drawl, I reckon that folksy label fits. This idea, quantum entanglement, shakes up our sense of space, time, and reality. Two far-flung things can be linked in a deep, mysterious way. Let's pull back the curtain on this cosmic magic trick. We'll see what entanglement is, why it seemed impossible, and how we proved it's real. No heavy math, just clear pictures. Then we'll explore how it fuels tomorrow's tech, from unhackable communication to revolutionary computers. The quantum world's a new frontier, the rules are different, and the sights are startling. Let's start with a simple thought experiment. Forget particles for a moment. Picture a pair of socks, one red, one blue. You put each sock in identical boxes, hand one to a friend, keep the other. Your friend travels thousands of miles away. You peek, red. Instantly you know they've got blue. No mystery there, just a preset fact. Einstein figured outcomes were decided in advance, hidden variables. But quantum coins are stranger. Made together, they ain't heads or tails yet. They live in a fuzzy both-at-once state until measured. The only rule, when measured, they must disagree. One heads, one tails. Measure one and it snaps to heads. Its twin, no matter how far, snaps to tails. Unlike socks, this wasn't decided beforehand. Both states are undecided until the first measurement collapses the possibilities. It binds their fates into one unified system, spooky but real. Not everyone was on board, least of all Einstein. He'd reshaped our view of gravity, space, and time with a local, sensible universe. Information couldn't outrun light. Entanglement seemed to spit in that cosmic speed limit's face. So in 1935, with Podolsky and Rosen, he fired back, the EPR paradox. They argued quantum theory was incomplete. Particles carried hidden instructions from birth, like socks pre-packed with color, preserving locality and killing the spooky link. Einstein insisted reality exists whether we look or not, he joked. The moon's there even if he ain't looking. For decades, the debate was philosophical. No clean test to settle it. Was the universe locally real or fundamentally non-local? The question hung like a storm cloud over physics. Peeking behind that curtain seemed impossible until a quiet breakthrough reframed the whole argument. The moment of truth. In 1964, John Bell turned talk into testable math. Bell's theorem, Bell's inequality, put a hard limit on any hidden variable world. If quantum predictions were right, real data would bust that limit. In the 70s and 80s, Clauser and Aspect took up the challenge. They created entangled photons and sent them to far-apart detectors. Settings changed faster than any signal could fly between them. No conventional communication, no cheating. Results rolled in and stunned everyone. Experiment after experiment violated Bell's inequality. Turns out the universe is as spooky as quantum theory said. Entanglement left the blackboard and entered the toolbox. Today, scientists harness it for real-world systems. One star player is quantum communication. Entanglement can make channels perfectly secure in principle. It's called quantum key distribution, QKD. Alice and Bob share entangled pairs. Their correlated results become a shared secret key. If Eve listens in, her measurement disturbs the state. Errors give her away. QKD's been run across city fiber networks, and even via satellites toward a global secure web. Banks, governments, and militaries are exploring it right now. You still compare notes over a classical link, but entanglement adds a built-in burglar alarm. Beyond comms, quantum computing grabs headlines. Classical bits are zeros or ones, billions of tiny switches. A qubit can be 0, 1, or both at once. Superposition. Entanglement ties qubits' fates together, the secret sauce. 2 entangled qubits represent 4 states at once. Add more, and power grows exponentially, beyond atom count scales. They tackle problems classical giants struggle with. Think optimization, physics simulation, and big number factorization. But qubits are delicate. Noise can wreck entanglement. Teams worldwide race to stabilize more qubits, from superconductors to trapped ions. We're early, like the 1950s for classical computing. Entanglement is the engine primed to tackle grand challenges. From Einstein's puzzle to tomorrow's power plant, entanglement's journey is wild. It reveals a universe profoundly interconnected at its roots. 2 once-linked particles can act as one system across vast distances. Principles are leaping from blackboards to blueprints, secure nets, quantum compute, and beyond. Quantum sensors promise sharper GPS, cellular-level imaging, and deeper stargazing. Some even suspect entanglement ties into space-time itself, maybe a bridge to unify physics. With each experiment, we edge closer to grasping what it all means. The future won't be built just on bits and bytes, but on this spooky, beautiful connection. The future, without a doubt, is entangled. Like and subscribe.